A couple students came in and said, we got some skewed results. I got 8 out of 10 wrong, she got 7 out of 10 right. When you look at it from that small of a sample, 10, it becomes the Max Crocs problem from 243. If you had me in 243, remember Max and his Crocs towards the end of class, we looked at how many times he got his Crocs on the correct feet out of 10. And you realize that there's a wide range of values that would be acceptable if you were guessing. So looking at the distribution, I ran dist fill. I ran dist fill on 0 to 10 for guessing. So there's basically a no % chance, a 0% chance that you're never going to get the right hand. There's also basically a 0% chance that you're never going to get, all 10 correct hand identifications. There's almost a 1% chance, which is still extraordinarily unlikely, to get 9 out of 10 right. Just like there's exactly the same probability that you get 1 out of 10 right. But as soon as you get between 2 and 8, this is where 95% of your data lives. So since that's where 95% of your data lives, anywhere between 2 and 8 would be considered, if you will, usual. Does that make sense? That would be considered, if you will, usual. So here's what I want to do. I want to put all of our class data together into one big collated chart. And on number 6 down there, on number 6, it's on the back side of your paper actually. What I'm going to do is we're going to make a little tiny distribution where you've got the number of times you got the hands identified correctly and then the frequency of that. And this is going to be our data we're going to work from. So here's number of times correctly ID'd. And then a frequency count. And it goes 0, 1, 2 up to 10 because that's basically what we've got. We're going to analyze you guys individually by the end, like your percentage of correctness. So what I want to do is, looking at what we did before, I want to do both things. I want to do, I can make this fancy, I want to estimate your percentage of correctness and also your percentage of correctness as a class. But right now, I want to answer this question, which is the average number of times we get it right out of 10. Does that make sense? So Bob, it goes back to your awesome point about compartmentalization, trying to figure out which one to run. I want to do the average right now. It's discrete data, but I want to do the average. So the question I have is, did anybody get no hands correct at all? Nobody got none correct. Okay, so that's going to be a 0 on that frequency.
Got none.
None got none. That's
double negative.
Well, none got none. Actually, it's not. It's just a statement. How many got 1 correct? 1 correct out of 2 correct. 2 correct out of 10. 2 correct out of 10. We got 1, 2, 2. Oh, I'm sorry, guys. Did you guys get either 0, 1, or 2 correct out of 10 in your trials? Okay, so we got 2 had 2 correct? No. 3 correct. I was in here. That was me. I think, Ken, right? That was 3. Yep. So we got 1. Are you accounting for me? Yes. Okay, so I'm not going to vote myself then. So we got 1, 2, 3, 4. 4 correct out of 10. 4 correct out of 10. 1, 2, 3, 4, 5. 6 correct. Excuse me, I jumped 5. 5 correct. I gotta keep going in order here. 5 correct out of 10. 5 correct. Exactly half.
I put your hand up before.
1, 2, 3, 4, 5, 6, 7, 8, 9. 6 correct out of 10. 1, 2, 3, 4, 5, 6, 7, 8. Love it. 7 correct. 1, 2, 3, 4. Love it. 8 correct. 1, 2. 9 correct. We got 1. And all 10 correct. We got 1.
Wow.
Beautiful, beautiful. This is exactly what I was hoping would happen. Now, do you remember there was a series of assumptions that we had to meet? There were a series of assumptions that we had to meet for one prop z ints. You had to have a binomial experiment. For 95% confidence, you had to have at least n times p bigger than 5. And there's a number of assumptions that are true for these kinds of tests too, but there's only 2 I want to keep verbalizing. I'm never going to make you write these down. I may have you do homework questions on them, but I'm never going to assess you in class on them. But I want you to think about this because this is the kind of stuff that makes sense when you're actually designing your own research studies. First, you have to have a simple random sample, which I know we don't have because you all came to stat class today. That's hardly simple random. But we got what we got. Number 2, there's that magical cutoff number of 30 data points. I care less about the 30 data points than I care about the shape of the data. So that's what I want to look at right now. Everyone, if you would, grab your TIs and get this data into your TIs in list 1 and list 2. That's what I want to do now, is I want to analyze our data in L1 and L2. That was kind of dumb, I should have just left. Zero, zero, two. So I'm going to do this. I'm going to swirl this over here, and I'm just going to erase this distribution right here.
Hey Sean, just a quick question.
Go ahead.
Like, why would I only have now L3 to L6?
Easy fix. Press stat,
Okay.
5, enter. Does it say done?
Yeah.
Go back. They're back now.
Okay.
Yeah. You just deleted them instead of clearing them. No big deal.
Oopsie, just kidding.
Easy fix. No, no, no. They weren't there before. You're right. It's just there's a bug in the system that allows you to delete lists for some reason. So now what I've got is I got the same distribution. In L1 is the number of times we got it correct hand identification. L2 is the number of folks that did that. If we summed up L2, that should tell us how many people actually participated in the experiment. The first thing I want to do is look at that data. I want to look at that data to make sure I've got a bell curve. Now looking at the data itself, I can kind of see a bell curve. Jamie, I remember you doing this last term in 243. You can tell by looking at it. Ish. I want to, just for practice, get a stat plot, get a histogram up on your TI. I'm going to go through this relatively quickly only because we did it so much in 243, but it'll be right here on this YouTube video if you need steps, and I'll verbalize it as I go through it. So cancel that, exit. Second y equals, plot 1, we're going to turn it on, turn it into a histogram, and you do want X list L1, frequency list L2. You do want that because we have our data in L1, but the frequency is in L2. So we got the stat plot on, we've got the type as a histogram, L1 and L2. Remember the quick and easy shortcut to get a real quick stat plot?
Zoom 9.
Absolutely, my friends. Zoom 9, get you a real quick stat plot. You can finagle at this point. I tend to like to. I'm going to finagle this so my x min is 0, my x max is 11, and my x scale is 1. This way, I get exactly 11 bars. I get exactly 11 bars from 0 up through 10. And there it is. And that could not be prettier. That looks like a bell curve to me, friends.
What did you put in for X max again?
X max 11. And the reason it's 11, this is a little bit counterintuitive, but because it has to go 0 through 10, 10 actually starts right here, Michael. And it needs the 11th spot to actually see that bar. I learned that the hard way, kind of working with this thing. We often put box plots above our histograms to identify outliers in 243. So real quick, and again, I'll make sure this is on the YouTube video so you can see it. I'm going to turn a second stat plot on, plot 2. And I'm going to make it a modified box plot. Set it up the exact same way, L1, L2. And again, if this feels fast, it might feel fast. We haven't probably done this in 4 weeks. You'll have a reference on the YouTube video. So there's a modified box plot with our data. What it's telling me is we do have one outlier. We do have one outlier according to the interquartile rule. And that one outlier is Miss Susie. You are unusual in that you got too many correct bisample statistics. That's something to concern yourself with when you're doing inferential stat. Because if we're trying to estimate the average number of times we get something correct, that could be pulling it to the right, couldn't it? Because it's an outlier. We're going to leave it in. We're going to leave it in, and then we're going to recalculate at the end with it taken out and see if it affects it greatly. It's only one sample data point. But that one data point out there is termed an outlier by 243 measures. So we'll come back to that. Fair so far? This is the only thing I kind of want you to do. Keep in the back of your mind. When I give you data in class, which I'll start giving you data sheets next time, the data's fine. It should be analyzed, it should be looked at, but it was collected okay. When you're doing actual research yourself, though, you have to make sure, oh yeah, I've got a rough bell shape. And I don't have too many outliers. One outlier is probably okay. Too many outliers is going to be skewing your data in an not okay way. Fair enough? We now have enough information. We've got our data in the correct place to actually answer the question, on average, how many times do we correctly identify the correct hand out of 10 trials? All we've got to do is run our t-interval now. Okay, I think this is the next question of the quiz, isn't it? What does it say? Does it say, create the 95% confidence interval? Yep, that's what we're going to do. That's the answer to the question. The 95% confidence interval for the average number of times we get the correct hand. So, keyword, average, which means we're going to be running a t-interval. You got it, Zoe, a t-interval. Run a t-interval, friends. So, tests, t-interval, t-interval. It's going to look exactly the same as before, except for one thing, right? L2. Exactly. The frequency list has to be changed to L2. Otherwise, it's going to average 0 through 10 all used one time. And you don't want that. You want to be able to account for the fact that there were more 5s, 4s, and 6s than 0s, 1s, 9s, and 10s. That's the only change you have to make. That's the only change you have to make. Now let's find out. On average, how many times do we get this right? On average, how many times do we get this right? Now, what did I tell you to round to? Whole number or a tenth? 1 decimal, okay? So, what I'm going to do is, you guys can just put one of these down. I'm going to calculate it. Well, actually, you don't have to calculate it with and without. We're going to leave Susie in, because your outlier is not going to change this result at all. We are 95% confident that out of 10 trials, we're going to get the correct answer between 4.7 times and about 6 times, right? 5.95, which rounds to 6 times, and 6 times. That's what that tells us when we group all of our data together. When we do 10 trials, assuming we're a good simple random sample, which I know we're not. I know we're not. I know we're not. But our data behaved properly. We've got a bell curve, 1 outlier. We're going to come back to why I'm saying we're not going to retest that. We don't have to. We can be 95% confident, 95% confident that we're going to get between 4.7 correct answers and 6 correct answers. You see what I'm getting at there, friends? Does this prove or disprove that we are guessing? I personally was guessing, because I couldn't tell where Ken's hand, over which one of my hands Ken's hand was. Can we disprove that we're guessing with this confidence interval? No, this is an inconclusive interval, right? Where would guessing be? If we were guessing, where would our average be? At 5. If half the time, or 5. This tank starts at 4.7 and goes to 6. So 5's in the tank. 5 is in the tank, which means the fish that represents, assuming our data is good, the fish that represents the average number of times we get it correct might be more than 5, in which case we support that we're feeling something. It might be exactly 5, in which case it supports that we're guessing. Or it might be below 5, which means it supports that we're doing worse than guessing. Since I have a choice of 3 possible places the fish could be, I put my hands up and I say, I have no idea what's going on. Which means I can't, this is an inconclusive confidence interval. It doesn't tell me anything's going on, but it also tells me nothing's not going on. It doesn't tell me anything. It tells me it's inconclusive. Is that fair enough? Check this out. You see how the average, though, is above 5? If I increase my sample size, and that average stayed in the same place, that's a big if, by the way. It might not. It might move. But assuming that average stayed at 5.333, what would happen to this tank, friends? That tank would get narrower, and eventually, assuming that the 5.333 stays where it stays, eventually 5 won't be in it anymore. And then we'll have statistical support to say that we're doing better than guessing. Is that, you see what I'm getting at there, friends? Susie, go ahead.
So is guessing always at 50%?
Yes, when you have two choices.
Okay.
If we had three choices, it'd be a third. Four choices, a fourth. But since you only have left or right, you only have two choices. Is that fair? Yeah. We're going to come back to that over and over and over again. Does that make sense, you guys? Oh, I'm sorry, you had a question. No question. Solid, solid. So this is an inconclusive interval, as it often is. We often get this beautiful bell shape. I mean, I just love that graph. And I said Susie might skew the results because she's an outlier on the high end. But if we pulled her outlier data value out, think back 243 now. If we pulled Susie's out and recalculated, what's going to happen to our interval, friends?
Shift more to the
It's going to shift more this way, isn't it? Maybe not a whole lot. It's one data point out of, say, however many there were. But it's going to move down, which isn't going to make it any more conclusive. The only way to make it more conclusive is if Susie was the one pulling the interval away from 5. That's the only way it could be more conclusive. So in other words, this experiment tells us nothing. But that's okay. We didn't go into it saying, let's prove or disprove something. We went into it saying, let's see what we see. Let's see what we see. Is that fair? So that's what we say. We cannot conclude anything. We don't know if we are feeling this any different than guessing. We might be, we might not be, we might be guessing. But this doesn't tell us anything because the 5 is actually in the tank. Well said, Bob. Well said. Cool? Does that make sense? Now what I want to do is I want to compare and contrast that with what we just got done doing, which is estimating the percentage of correctness. The percentage of correctness. So basically, is this CI evidence of existence of detection of the energy field? No. It's not evidence of anything. Of course, the experiment itself is fraught with inconsistencies. But assuming the data was okay, even if the data was perfect, it still doesn't tell us yay or nay. So it's inconclusive, and this happens all the time.
Susan was.
Well, that's one data point. And how often does that happen? Well, I had this ant one time. One data point. I'm talking about average. I'm talking, you can't average one. Fair? Fair? Good? Okay. So basically, the answer to that one is no, we can't conclude anything. Now, let's do percentage of correctness individually and then as a class. So all you guys that were participant A, let's calculate your percentage of correctness. This is number 11A. So in other words, it's a percentage of correctness. So now, good Zoe, this guy right here, percentage of correctness. So all of us, stat tests, who do we go to now? What, good, is it 8? One prop Z in, there he is. Now we're all going to get different results for this. Me, I was 3 out of 10. I was 3 out of 10. There's my percentage of correctness. Can I prove or disprove that I was guessing? Can I prove or disprove I was guessing based on my interval? I am 95% confident that I am going to get it right between about 2% of the time and 58% of the time. That doesn't include anything because 50% is in there. It's in the tank again. Is anybody's tank not including 50%? Bob?
You go to 2.
When you get 2, Bob and Ashley ran 2. They got it right 2 times out of 10. Check this out. 2 times out of 10. They're doing worse than guessing. Now, of course, take that with a grain of salt. 10 trials. 10 trials. Take that with a grain of salt. Hey, which means the folks that got 8 out of 10, you're doing better than guessing, aren't you? 8 out of 10 would be the complement of that, right? 8 out of 10. You guys are doing better than guessing. You're getting it right at least 55% of the time, which is better than guessing 50% of the time. Hey, but the point is that with that small of a sample size, you have to accept a ridiculous margin of error, don't you? Yes, that's why we're going to collate our data now. We're going to collate our data now. Please, Christian.
So for yours, when you wrote it out, would it be like between 15 and 58%?
1.5, 58%. It was 0.015.
Oh,
So 1.5% and 58%. Exactly. So, for example, this one right here, if you wrote it out, and Christian, your choice. You can put 0.55 to 1.04. That's kind of silly, isn't it? It's over 100%. But that's okay. A margin of error doesn't know that you can't go over 100%. It's mathematical. It's okay to go over 100%. I have no problem with that. Fair? Fairish? Getting there. So all of you are going to have your own confidence intervals for your individual performances on the exam. And now we're going to do the entire class. So while you guys do A and B, let me get the total number that we're going to need for our experiment here. Yeah, Jamie, go ahead.
Can I round the percentages?
Sure, round it to the nearest whole percentage if you want to. Now you guys, I just did this real quick to get us the number we're going to need for 11C. Because 11A is person A's percentages. 11B is person B's percentages. And then 11C is the entire class's percentages. So in other words, you have to run this guy again for the entire class. So just so you know, the numbers you need for that, we got 192 right. Out of 360. So the reason, what I just did was I ran 1 bar stats. So basically what 1 bar stats did was it did 0 times 0 plus 1 times 0 plus 2 times whatever plus 3 times whatever. It added up like we did back in the day at 243. So quick and easy, it's 192. We identified the correct hand 192 times. And there were 36 of us, but we each did it 10 times. So it's 192 out of 360. Those are the numbers you need for your collated class experiments. So run it again. 1 prop z int. How did we do as a class? Is that evidence that we're not guessing? No. Is that evidence that we're not guessing? No. No, that's almost identical to the interval that we got for the t interval, but it's a percentage instead of an average. We can be 95% confident that as a class, we will get the correct hand between 48% of the time and 58% of the time, which includes 50%, which means that once again it's inconclusive. It wouldn't be inconclusive if the fish wasn't in the tank. In other words, if the parameter we're comparing, the guessing parameter, was above or below. But it's right smack in the tank like it is right here. So the problem with that is we can't conclude. It's an inconclusive interval, and that's okay. This happens all the time in statistical studies. This tells you something in general. This tells you something. Sometimes you want inconclusive intervals if you're trying to show that a drug has no side effects, for example. You don't want to see that it does have side effects. You want to see that it doesn't, unless the side effect is gives you something else, like
marketable.
Exactly, which is marketable. That's what I learned in 243, where Viagra came from.
Yes.
You heard that, right, YouTube? Viagra came from, Michael?
It was a heart medication.
Heart medication. Gone horribly.
Wonderful side effect. That
Right?
decided to use.
Wrong? I don't know. You decide. You decide. How's that? So the big takeaway, are you trying to estimate an average? T interval. If you're trying to estimate a percentage, Z interval. That's the big takeaway. Bob, thank you for you synopsized about an hour ago. This is just more practice with it. If you want that to be an in-class quiz, which I think you all should, go draw your 10s on it. Make sure your names are on it. Add it to the same pile. What's that mean? If you don't mind returning the pennies too. So friends, I don't see you again till Tuesday. I am very, very depressed about this.